Chapter 3, Polynomial and Rational Functions, Section 3.4, Real Zeros and the Rational Zeros Theorem. A polynomial function f of degree n can have at most n real number zeros. And these zeros correspond to the x-intercepts of the graph of f. So anytime you're talking about real number zeros, they can always be identified as x-intercepts on the graph of the function. In attempting to identify these zeros, it would be helpful to be able to list the possible rational zeros of f. Now, rational numbers are a type of real number. Rational numbers are the numbers we usually think of as ordinary fractions, such as 1/3, negative 7/5, etc. So by getting a list of possible rational zeros, we can we sort of have a starting point in finding all of the possible zeros of a polynomial. And in finding zeros, it's basically equivalent to solving an equation. So we're really looking for solutions of equations. The following theorem provides us with such a list of possible rational zeros. And this is the rational zeros theorem, or RZT for short. Let f of x equal a n x to the n, that would be your leading term, plus some other terms, plus a constant term, a0, be a polynomial function with integer coefficients. Now that means that the a's have to be non-fractions. That is, numbers such as 1, -1, 2, -2, 3, -3, and so on. So we want to have our function expressed in a form where the coefficients are integers. If the rational number p over q, expressed in lowest terms, is a zero of f, then p must be a divisor of the constant term a0, and q must be a divisor of the leading coefficient a sub n. So it turns out that if a particular rational number is a zero of a polynomial function, then in lowest terms, its numerator and denominator must be divisors of the constant term and the leading coefficient, respectively, of the polynomial. Let's look at example 1. List the possible rational zeros of f of x equals negative 3x cubed plus 4x squared minus 8x plus 12 according to the rational zeros theorem. So we want to identify possibilities for p and q for our rational zero or possible rational zero p over q. So according to the theorem, the p's must be divisors of the constant term. So in this polynomial, the constant term is the 12. And the q's must be divisors of the leading coefficient. So that would be the -3. Usually we see the leading coefficient written with the first term, assuming that the powers of x are in descending order, which is typically the case. So the p's would be divisors of 12. Now the divisors of 12 are plus or minus. We could have both positive or negative divisors. For 12, there's quite a few divisors. There's 1, 2, 3, 4, 6, and 12. And then for the q's, we're talking about divisors of the leading coefficient, -3. Well, here there are fewer because 3 is a prime number. Plus or minus 1, or 3. So the possible rational zeros are formed by taking all the p's divided by all of the q's and listing these systematically, plus or minus. Let's start by dividing all of the p's by q equals plus or minus 1. So that would be 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1. In other words, just 1, 2, 3, 4, 6, and 12 again. And then also take all the p's and divide by q equals plus or minus 3. So that would give us 1 over 3, 2 over 3, 3 over 3, 4 over 3, 6 over 3, 12 over 3. Again, plus or minus. Keep in mind the plus or minus that I wrote out in front applies to all of these numbers. Now, in the second batch of numbers, when we divided by 3, we see some repetitions with numbers we've already listed. So we don't want to list those twice. So 3 over 3 is 1. So I'm just going to scratch that out. We don't need it. 6 over 3 is 2. We've already listed that, so we don't need that. 12 over 3 is 4. We've already listed that. So counting what we have left, we have 6, 7, 8, 9. It's actually 18 possible rational zeros of this function. That's the 1 through 12, 1/3, 2/3, and 4/3 plus or minus. So there's twice as many as what we've listed if you include both the positives and the negatives. Now, there are obviously not 18 zeros of this function. This is a third degree polynomial function, so the maximum number of zeros it can have is 3. So what do we get from this list? If we look at the paragraph below, what the rational zeros theorem gives us is not a list necessarily of actual zeros, but of rational zero candidates. And as a result, it indicates which rational numbers also are not candidates. So what we're saying is that if our function has any rational zeros, they have to be numbers in this list. So these are the candidates for rational zeros of this polynomial. And if numbers do not appear in the list of p over q's, then we can rule them out as possible rational zeros of the polynomial. So for example, the rational number 5 could not be a zero of f since it doesn't appear in our list. So we can definitely rule out rational zeros. We can't necessarily rule any of these in unless we actually prove that they're actually zeros of the polynomial. Let's move on to example 2 and actually find some zeros. Use the rational zeros theorem and synthetic division to find all of the real zeros of f of x equals 2x cubed plus 7x squared plus 2x minus 3. We're going to begin by listing the possible rational zeros of this polynomial. And so again, we need to identify the p's and the q's. The p's are the divisors of the constant term -3. And that's just plus or minus 1 or plus or minus 3. The q's are the divisors of the leading coefficient, +2. That's just plus or minus 1 or plus or minus 2. So if we divide all the p's by all the q's, we get the set of all possible rational zeros. So 1 over 1 and 3 over 1 plus or minus just gives us 1 and 3. And then 1 over 2 and 3 over 2. And again, we're assuming plus or minus all of these. I just write the plus or minus once sometimes, but that actually applies to all of those numbers in that list. That's a total of 8 possible rational zeros. Now, this being a third degree polynomial, the maximum number of zeros we can find would be 3. So these are certainly not all zeros, but if this function has any rational zeros, they have to be numbers from this list. So we can test some of these numbers to see if they are actual zeros of f. And one way that we can do that is to use synthetic division. For example, if x equals 1 were a zero of f, then x minus 1 should be a factor. So if we do a synthetic division using 1, thinking of x minus 1 as a factor, along with the coefficients of f, which are 2, 7, 2, and negative 3, we can test to see whether 1 is a zero of f. So we bring down the 2, we multiply 2 times 1, we add 7 and 2, we multiply 9 and 1, we add 2 and 9, we multiply 11 and 1, we add negative 3 and 11. Separating that off, that gives us 8. What this is telling us is that x minus 1 does not divide evenly into f of x because the remainder is non-zero. We could also say that f of 1 is equal to 8, so 1 cannot be a zero because by the remainder theorem, f of 1 would have to equal 0, the remainder would have to be 0. So 8 is actually what the value of f of 1 is here. So 1 is not a zero, and we can eliminate it as eliminate it from our list. Now you can see obviously we have some limitations with this approach because we have to repeatedly use synthetic division. But let's just try another one and see if we can find one that works. If I use negative 1, again I'll just list my coefficients 2, 7, 2, and negative 3. Bring down the 2, multiply negative 2, add 5, multiply negative 5, add negative 3, multiply positive 3, add 0. So 0 is f of negative 1. Therefore, negative 1 is a zero of f. Now, we actually get 2 for the price of 1 here because, actually 3 for the price of 1, because not only do we know that x plus 1 is a factor, so is the quotient that we see here. The quotient has a degree 1 less than the degree of f, so this would be 2x squared plus 5x minus 3. If we set that equal to 0 and solve for x, we can hopefully find the remaining zeros of this polynomial. And indeed, we can just factor using 2x and x, 3 and 1 plus and minus. That gives us the correct factored form. Setting the factors equal to 0. And solving for x gives us 1/2 and negative 3. So the actual rational zeros of this polynomial would be negative 1, 1/2, and negative 3. I'll make some concluding comments about this example at the beginning of the next video.